we, in this video, we will try to generalize the concept of partial derivatives along any given direction, not only along coordinate axis. So we will try to find partial derivatives along any direction. So here, that is called as a directional derivative because you are finding derivative along given direction. So that's why we call this as a directional derivative. So directional derivative of phi, so phi is a scalar function here, at some point x naught, y naught, z naught along the direction of vector u bar. Okay, let's quickly recall how we find partial derivative with respect to x or partial derivative along x-axis. Okay, so along x-axis, so this is a vector. This is a unit vector along x-axis, 1 I bar plus 0j plus 0k. So here this is our x-axis, y-axis and z-axis. Suppose here is our point P x naught, y naught, z naught, which lies on this surface phi. So whose x coordinate is x1, that is this distance, y coordinate is y naught, that is this distance, and the height is z coordinate. Okay, now for a small change t at x naught, y naught, z naught along the direction of x-axis, that means this. So this direction is same as x-axis. Okay, we are changing it by uh, let's say t along x-axis only. Okay, so we get new point q whose coordinates will be, so its x coordinate will change now, it will become x1, y coordinate, so this distance, that is y1, and this height is z1. But you can observe here that this distance, this y1, this length and this length, they are same. Y1 and y0 are same. Similarly, z1 and z0 are same because the change is along x-axis only. So only x coordinate changes, and that is why same distance, this same distance here t. Okay, so here we get x1 as x0 plus t, y1 as y0, and z1 as z0. So here all these x, y, z are functions of t. Okay, so these equations here represents a parametric equation of curve, let's say C, on phi joining points P and Q. Now, so how you find a derivative? So basically, we find phi at new point, that is at Q, minus phi at P divided by T, and limit T tends to 0. As along the curve C, phi is a function of x, y, z, and that is a function of t only. So this is nothing but a derivative with respect to t. So this is d by dt of phi, and because phi is a function of x, y, z, which is a function of t, so by chain rule we get this as delta phi by delta x into dx by dt plus this delta phi by delta y dy by dt plus delta phi by delta z dz by dt. Okay, now we already knew that xt is x naught plus 1t, therefore dx by dt is 1, dy by dt will be 0 because y is y naught plus 0t, and z is z naught plus 0t, so dz by dt is also 0. So this expression gets reduced to this delta phi by delta x plus 1 plus delta phi by delta y into 0 plus delta phi by delta z into 0, which is equal to delta phi by delta x only. This is what a partial derivative of phi with respect to x. But it is a particular case. Here we are finding derivative along x-axis only. Now we will try to generalize this. How to find derivative along any direction, a direction of vector u bar. So let u, so as we are interested in a direction of vector, so we'll take unit vector along a vector u bar. So here this is u cap represents unit vector along this vector u bar, which is u1i plus u2j plus u3k. Let's say this is the direction of our vector u bar. It is different, it may be different from our coordinate directions of coordinate axis. Okay, so this is x-axis, y-axis and z-axis. Again, suppose this is our point P x naught y naught z naught, and so its x coordinate is x naught, y coordinate is y naught, and z coordinate is z naught. Okay, for a small change t at x naught, y naught, z naught along the direction of vector u bar. Now here we are changing along the direction of vector u bar. So it may be the change will be in this direction. Okay, the small change t along this direction. So we'll get new point q x1, y1, z1, whose x coordinate is now x1. Now see here the x naught x1 is x naught plus t times u1. U1 is what? It's x component. So when we change u by t along x-axis, it gets changed by t times u1. Similarly, along y-axis, so here this distance will be t times u2. It will get changed by t times u2. So this is its y coordinate, y component. Okay, y component, y will be changed by this amount. And similarly, z1 will be t times u3. Okay, so these are the corresponding changes. Now, so again here, these equations of x, y, z represents parametric equation of curve C on phi joining these points P and Q along direction of this vector u bar. Okay, so again by definition of derivative, this is limit t tends to 0, we'll evaluate phi at Q. So this is these are the coordinates of point Q, minus phi at P divided by T. Okay, so along C, phi is a function of x, y, z, and that is a function of t. So this is same as d by dt of phi at t naught. Now, because phi is a function of x, y, z, and x, y, z are functions of t, so by using chain rule, we get this expression here, which you can write as a dot product of these two vectors. So this is how we can write this as a dot product of these two vectors. Okay, now here x is x naught plus t u1, therefore dx by dt is u1. Similarly, dy by dt is u2 and dz by dt is u3. So when you put these expressions in this bracket, we get the first bracket as it is into u1i plus u2j plus u3k. But what is this? This represents our vector u cap. So you get this dot product of the first term here with u cap. Okay, now here this bracketed term will denote it by, so this is an operator here. Okay, this bracketed term is an operator. We call that as a vector differential operator, and we denote that by del. So here del is this dabba by dabba x of I plus dabba by dabba y of j plus dabba by dabba z of k. So this becomes del phi evaluated at x naught, y naught, z naught dot product with u bar. This is what a directional derivative of phi along the direction of vector u bar is. So this is how you find directional derivative. So what we have to do here, we'll apply this vector differential operator del on our scalar function phi, and then evaluated that at point x naught, y naught, z naught, and then we'll take its dot product with a unit vector along vector u bar, that is u cap. This represents a directional derivative of phi along direction of vector u bar. Now see, and it is denoted by del phi dot u cap. Okay, now see, so what we have studied, what is the directional derivative? So directional derivative of phi along the direction of u bar is represents rate of change of phi in the direction of vector u bar. So this gives you rate of change of phi in the direction of vector u bar, that is a slope of phi in direction of vector u bar. Okay, so for example, let's find directional derivative of this function phi along x-axis at point x naught, y naught, z naught. So this is, as you know, this is a vector form of our x-axis. Therefore, del, so this is our vector differential operator, del phi dot this u cap. So it is what? Because this this is 0 here, 0 times j and 0 times k. It gets reduced to del by phi by del by x at x naught, y naught, z naught, which is nothing but what? Or partial derivative of phi with respect to x. So the partial derivative of phi with respect to x or y or z are just a special cases of these directional derivatives. Okay. Here we'll discuss one of the very important property of directional derivative. When the directional derivative is maximum. Okay. So here you see why we are discussing about maximum directional derivative. It's because a directional derivative is a dot product of two vectors, del phi and vector u cap. Now look at this dot product of a and b. It is equal to magnitude of a into magnitude of b into cos of theta. So when this a dot b will be maximum, so whenever this cos theta is maximum, right? Now when this cos theta is maximum, maximum value of cos theta is 1, and when theta is 0, we get that maximum value. So that means this a dot b is maximum when a and b are parallel. So when you take dot product of two parallel vectors, so that dot product will be maximum. Oh, in this case, our directional derivative is del phi dot u cap. So when this will be maximum, when del phi and u cap are having same direction. That means if we find directional derivative along direction of vector del phi, so it will be maximum. Okay, so along the direction of vector del phi we get maximum directional derivative, and the direction of del phi is always point towards normal to the surface phi. Okay, and the value of maximum directional derivative is mod of del phi, because here this u cap is a unit vector, so its magnitude is 1, so this reduced to magnitude of del phi only. This is the maximum value of directional derivative is del phi, and it is along the direction of vector del phi. Okay, that means slope, that means along the direction of vector del phi there is a maximum slope, or rate of change of phi along the direction of del phi is maximum. Now here we'll discuss what is a gradient of phi. Okay, so we find gradient, we define gradient as this del phi. Okay, we operate this vector differential operator del on scalar function phi, so we get this. This is a vector. Okay, this is a vector quantity. Now we know that vector has two components, direction and magnitude. Okay, so what is the direction of this? What is the direction of grad phi? What direction it gives you? Okay, it gives us a direction along which function changes most rapidly. That is what we have discussed just now. Along del phi, rate of change of function is maximum. In which direction we get maximum directional derivative? Along the direction of del phi. So del phi is nothing but grad phi, right? So grad phi gives you direction of maximum change, or it gives us a direction along which function changes most rapidly. Now second component is magnitude. So what magnitude tells us? So it tells us how rapidly that function changes along the direction of del phi. Okay, so basically grad phi tells us, so grad phi gives direction of maximum change, and its magnitude gives the slope along the direction of maximum change. Thank you.